In this video, we discuss area computations in polar coordinates. Let's start with our new coordinate system, polar axis and the pole. Given piece of graph, we first check area of a sector region like this. Suppose this angle is alpha, this angle is beta. In polar coordinates, we slice the region like this. So between angle alpha and beta. We come up with n slices. Now, the idea is we want to obtain an expression for area of one strip, one slice, and add them up. Let's enlarge this strip and place it here. So this can be, since this is the angle increment d theta is very small, very small, so we can consider this approximately as a circular sector, meaning this is part of a circle. This way, assuming the length is r at any angle theta. From geometry, we know the arc length here is r d theta. Now, what's the area of this tiny slice called, say, dA? Well, it's easy to see. Approximately, if we place a congruent slice underneath, reversed, so this would be like approximately a rectangle. Area of this rectangle would be length times width. Length times width. Therefore, the actual area of the strip will be half of this. So it's a half r d theta square. Now the total area will be the sum of all those. So using our Riemann sum notation, it would be half r square d theta. You can use delta theta. And in strip, send the n to infinity using our definite integral notation. Maybe alpha to beta. We start from alpha. That's the first strip, and stop at beta. So this definite integral would give us the area of this region. Area equal to half alpha to beta r squared d theta. Now, this is a formula for area of a region with the pole at the tip of the region. More generally, if you have region between two graphs, So this is alpha, this is beta. Here's our region. We still slice like this. This time, the strip we pick up will be here. So the key is again to try to figure out area of one strip, then add them up and send n to infinity. Now this region is like the difference between the long sector and the short sector. So all we need to do is to basically find the area of each and subtract. According to our calculation, the long one, the green one, let's call this as R out. I will explain why I call it R out. I call this as R in. So as I was saying, according to our analysis, area of this longer sector is half R out square d theta. Well, area of this shorter one, the red one, is half R in square d theta. Let's simplify this a little bit. So this expression would give us the area of the strip between two graphs in blue. I call dA. Total area, of course, is then the sum of all those areas of strips. We add from alpha to beta, R out square R in square d theta. That is general version. Now I call this general version because this is like a special case of this one. When the R in is here, if R in is 0, we will have just one curve involved. That give us the formula there. Now let me briefly explain why I call this as R in, this is R out. How I determine R in, R out is start with a new graph. So this is a graph, there's another graph. I'm considering the area of the region between this graph and between alpha and beta. Now, of course, we have to know alpha, beta. That's what we use for the limits. Starting angle, terminal angle. Let's just talk about how we determine R in, R out. That's important. That's what we need to set up the integrand in the definite interval. Well, imagine yourself standing at the pole and shoot toward the region. If you do that, you're going to go through the region, entering the region from this curve. So I call this as R in. Coming out from this curve. So I call this as R out. Now we always shoot to determine the R in, R out. Alright? In addition to R in, R out involved in the definite interval for the area, there's alpha beta. or if it's clearly marked between the regions between rate theta equal to r, rate theta equal to beta, then it's clear, right? If it's not like this, how do we determine alpha beta in different cases? Well, generally, let's see. If there's a region how I do it is to kind of use a pair of chopsticks to try to pick it up. Where I place chopsticks down here determines the angle alpha. The chopstick I place here will determine beta. So I'm a Chinese, so this chopstick analogy comes just very naturally. Pick it up, and measure it up. That's alpha, that's beta. Once you determine your range angle alpha to beta, then shoot. You find your R in, find your R out. Now you see, if your region doesn't even have to be perfectly between two rays, looks like this. What I mean is the pole is at the border of the region, and you still use chopsticks to pick it up. This angle, which would be like a negative whatever, so that's going to be your alpha. This angle is your beta. You always measure your angle starting from the polar axis. So this is going to give you alpha beta, just like how we would do it here. And then the shooting analogy, well, you stand here, you shoot, you're at the border, so your R in this case will be just 0. Then of course you shoot, you hit the graph. In this case, say there's only one graph, so that's your R or R out. That would be like this case. Well, before I show another situation, I want to comment on determining the alpha beta. In this case, at the pole, R is 0. So to determine your alpha beta, usually what you do is to set R to 0, because here R is 0. So you set R, which is a function of theta, to 0, and the solve. You get solutions. Then depending on the position of the region, you pick out reasonable angle solutions as the angles alpha beta. I'll show you this from our examples. That's how you usually determine your alpha beta. Not usually based on observation. It looks like 45 degrees, looks like 90 degrees. It doesn't work that way. So you have to do the algebra to determine precisely the angles involved. You need alpha beta. In this case, usually how you determine alpha beta is most of the time you have two graphs, so you would find the intersection. You have your R out, R in, set them equal to each other, because at the intersection the R are the same, so you can find the solutions. Again, based on the position of the region, you find reasonable answers as your alpha, as your beta. Now let's see another special case where we try to determine alpha beta R in, R out, and so on. This is the case when the pole is completely inside the region. This time, this chopstick analogy doesn't work well because it doesn't make sense how you pick it up. Well, we try. How I look at this is, I would imagine two chopsticks all placed along polar axis. Try to open up to pick up the region which is here. So this will give me, say, the starting angle would be 0. Alpha would be 0. The other one, second chopstick is placed at 2 pi. So from 0 to pi. And this makes sense because your theta will start from arc to 0, going around to cover the whole region. So alpha is 0, beta is 2 pi. Actually, anytime your pole is inside the region, you have to always go from 0 to 2 pi. And shoot, well, how do we shoot? We stand inside the region, so of course we are already in the region. R in is 0. We shoot out, hit the graph. That's R out. 0 is R in. All right, those are the cases, different cases where we try to determine angles involved, alpha, beta, or R in, R out. In order to set up the definite interval for area of region in polar coordinates. Now, before we get into area computation problems, we need to talk about graphing in polar coordinates. Well, as you can see, no matter what case, simple sector region or region between graphs, or this, we have to know the graph. We have to know the border, which usually is graphs of some polar equations. So how do we graph polar equation? You're not able to graph the equation involved, you're not going to be able to see region, and there's no way you can determine your angles, R in, R out. So it's important that we talk about graphing. How do we do it? Well, one way is use calculator. If you have a calculator that's capable of graphing polar equation, use it, go ahead. If you don't have a calculator, you can always use the old table method. How it works out is just like before. You pick up various angle theta, plug in, generate a corresponding R value. Table method. Input, output, whatever angle, pick up depending on the interval. Pick up angles in between. Pick up, for example, R theta equal to 0. You calculate theta equal to pi over 6, which is like 30 degrees. Plug in, calculate. So one angle, one R value, R theta. So we get a pair, or theta R. We usually put R first. R theta, R theta, R theta. In polar coordinates, you find your when theta is 0, R is, say, whatever value. When theta is pi over 6, 30 degrees, R is whatever value. Another angle just increases a little bit. This way you can generate a bunch of points and kind of trace out connecting dots in a graph. This method is actually commonly used when graphing calculator is not available. Just a lot of work. Well, again, you probably still need some sort of calculator in order to evaluate polar functions, which usually involves trig. So anyway, now one tip is, in order to get a good idea of what the graph looks like, try to pick up enough angles between the given interval. Usually it's a 0 to 2 pi, or if it doesn't say any range from 0 to whatever, it's 0 to 2 pi. So you would probably have to pick up some angles in the first quadrant less than 90 degrees, some angles from the second quadrant between 90 and 180. So all four quadrants pick up. This way you get enough points that to show you more correctly, more accurately what graph is like. Okay, so that's the second approach. First calculator, then table. Another approach we sometimes take is to convert. For example, r equal to 2 cosine. So we multiply both sides by r. We learned to convert equations before. Now r cosine becomes x. So I have 2x, and r squared is x squared plus y squared. And if you move 2x over completely square, you see a circle. And we'll see example later on. Just so you know, this is one option. Sometimes we use it. Most of the time, it's not working because even though we may be able to convert, the converted equation is just so complicated. I have no idea what kind of graph it represents. If it's a straight line, circle, it's a simple, common equations, yeah, we'll be okay. Anyway, so this is how we graph: calculator, table, or through conversion. Now let's actually see some example. Sketch graph, polar equation, r equal to theta, or r equal to whatever function of theta. This problem, we're given the interval. Theta is supposed to vary between 0 and pi, so we're going to try to just come up with a graph within this range. Now first example, r equal to theta, I'm going to use the table method. We'll try to come up with a sketch. So you do the table. This is the input, this is the r. We can go from 0 to pi, so try to pick up some angles from first quadrant, angles from second quadrant. Whenever possible, always pick up 0. R equal to 0, theta equal to 0, r is 0, so we are here. Then pick up angle pi over 3. About the 60 degree. But theta would theta are the same. So anyway, so just plug in, evaluate. What this means is when the angle is pi over 3, the r value, which is slightly less than 1, because pi is a 3, more than 1, sorry. Pi is a 3.14, so we just measure it up. Say it's here, assuming this is like a 1 point something, or pi over 3. Then we pick up pi over 2, which is here. Plug in. The value is about 1.7. Now this is almost 1, so 1.7 is approximately up here. So this is the angle pi over 2. So pick up a point here. And this is the idea. As you can see, as angle increases, the R value increases. So we can imagine whatever angle we'll pick up here, and this. So we expect a graph like this, like a spiral thing. That's approximately what the graph looks like. So table method. So the idea is create a table. Of course, in this example, the function is really simple. Function is R is the same as theta. If it's different, expression in theta, you just evaluate to generate those R values, which represent the distance along the ray corresponding to each input angle. Next, we can do try to come up with a graph through conversion. This time we multiply both sides by R, because there's a sign on this side. The sign on this side, you multiply by R, you get the Y. Nicely, very simple Y. Where this is x squared plus y squared. Now we're going to complete the square. Okay, move the 4y over. 0. Add square of half of this number. That's a -2 squared. So we add to both sides. Algebraically, this is perfect square. So from the equation we see graph is a circle centered at 0 to radius 2. So this is 2 in x, y coordinate. We expect graph to be like this, a circle. So polar coordinate r equal to 4 sine represents a circle centered at 0 to coordinate. Radius 2. This radius is 2. Of course, you have calculator. Go ahead, use calculator. Alright, this is basically how we graph. We'll see how to graph in some of the examples too. Now, let's see area computation. The first example, we're going to find area bounded by curve, which is graph of r equal to 1 plus cosine. I'm going to use the table method. Conversion will not work. If you convert, you're going to get something really nasty. Don't have a calculator, so let's just use brute force. Table. Get some idea, okay? Input, output. So I pick up a 0. When theta is 0, plug in r is 2. Theta is 0. Well, this is the pole. Angle is 0. R is 2. Say it's here. Let's see. Let's pick up, say, theta equal to pi over 6. Not pi over 3. Because I know cosine pi over 3 is it's 1/2, very simple. So it's 1/2 plug-in for cosine. It's 1 plus is 3 over 2. So it's like 1.5. At angle pi over 6, which is approximately 60 degrees. the value is 1.5. Now this is 2, so 2 will be here, 1 will be here, 1.5 will be here. This location, we pick up pi over 2. Cosine pi over 2 is 0, so add pi over 2, this is 1. Right. Let's pick up pi. Cosine pi. Well, actually, before we pick up a pi, we can pick up some angle up here. But you'll see. Okay, let's get a pi first. Then get some idea, what it's going to be without actually doing some calculation, picking up a different angle. Say at pi, cosine pi is -1, so wait, add pi over 2, 1 plus cosine is 1. Add pi, it's 0. So the question is, what will be the R when it's between pi over 2 and the pi? I don't have to do any computation. You can kind of estimate, because look at the graph of cosine. Look at the graph of cosine. This is pi over 2. This is pi. So like we said, at pi over 2, cosine is 0. At pi, cosine is -1. So in between, we imagine the value to be between -1 and 0. -1 and 0 add to 1, so it's slightly less than 1. Now this is 1, this is 0, so we expect maybe values like that. Between pi and 3 pi over 2. Of course, you have a calculator, not the graphing calculator, just calculator. You can calculate cosine values at a different inputs. You can probably have more values here, because I'm using the graph of cosine to help me figure out value. I can get away with not having to do a whole lot more computation. So, well, at the 3 pi over 2, I see cosine is 0. The angle 3 pi over 2 going around now. Plug in. At the 3 pi over 2, R is going to be 1 plus 0. So it's 1. Then, of course, we're going to ask, what happened between pi and the 3 pi over 2? And I rely on the graph of a cosine, which gives me the values for this term. According to the graph, the cosine is going to be between -1 and 0. So when the angle is between pi and the 3 pi over 2, it's a 1 plus number less than number between -1 and 0. So the sum is between 0 and the +1. That's why I can figure out, if I pick up some angle here, it's going to be something between. It's increasing. You can see the cosine is increasing, so the R will increase up to this. To continue with this, we come up with our graph. Starting from theta equal to 0, increase. Now, is this actually a hard shape? I don't know, but I know it goes around like this. Alright, so this shows you again how to graph using the table method. Well, this is a area computation problem. So we got the region. See the region now? And also it's clear the pole is actually at the border. With clearly the region showing, can set up our definite interval. So half alpha beta. Now this is at the border, it goes around, the angle actually goes around, so we go from 0 to 2 pi. Now determining R in, R out. Well, we shoot, the pole is at the border, so R in is 0. We shoot, the graph is R out. So 1 plus cosine R out squared 0 R in squared d theta. Now, this is the definite interval for area of this region. The rest is to evaluate this trig integral. This trig integral. So you simplify it. So 1 plus 2 cosine theta plus cosine squared theta d theta. Find the antiderivative. Simple integral. Integral of 1 is theta. Integral of cosine is sine. Integral of cosine squared is half theta plus 1/4 sine 2 theta. Now I want to verify. Let me check my formula. Integral of cosine squared, yes, it's half theta plus 1/4 sine 2 theta. It's 2 pi plug in. 2 pi plug in for theta. 2 pi plug in for theta 0. 2 pi plug in for that is pi. 2 pi plug in is 0. And then plug in 0 for theta. Everything is 0, so we get big 0. So the final answer is 3/2 pi. Alright, this is an example where we graph the involved curve using the table method. Once we have the region inside, the rest is simple. Just determine the alpha, beta, shoot to determine R in, R out, to set up the definite interval of error. Next, we calculate the area bounded by one loop of graph of this function. And this function is not very easy to graph by hand using table method. You would have to pick up a lot, because for 3 theta you would have to pick up a lot of angles in order to capture the actual graph. If you have a calculator, that's good. Well, this problem we are giving a graph, just because it's not easy to do it without a calculator. So we want to find area of region enclosed by only one loop. It's supposed to be symmetric, so it doesn't matter which one you want to pick up. Say we pick up the first one. And it's clear the pole is at the tip of each petal, right in the middle. Now our formula is always half alpha to beta r out square r in square d theta. So we need to figure out the angles alpha beta and also r in r out. How we do it is to try to determine at what angles first r will be 0, because when we start out here, that's r alpha, some angle here which may or may not be actually 0. Just because it looks like we start from 0 doesn't mean it's always 0. It's got to be correct. The correct way to determine those angles involved through doing algebra. So we set r2 equal to 0 and solve algebraically. Divide by 3, so the equation is the same as sine 3 theta equal to 0. Now, what are the solution of this equation? Let's see the graph of sine. Start from 0, this angle, whatever we call beta, is going to be will be positive. This is why we only care about the graph of sine on the positive side of x-axis. Okay, well, look at the sine. Sine is 0 here, sine is 0 here, pi, 0, 2 pi, 3 pi. Now, how many intercepts we need? Let's see. Okay, from the equation we can tell for this expression to be 0, the 3 theta could be 0, 3 theta could be pi, 3 theta could be 2 pi. Now, I'm not going to get more unless I have to. Let's have this a 3 for now. So this means theta will be 0, theta will be pi over 3, theta will be 2 pi over 3. According to the graph, it makes sense now. The theta equal to 0 must be this angle. Theta equal to 3 pi, theta equal to pi over 3 will be this angle. As a matter of fact, the same order, theta equal to 2 pi over 3 must be this angle. Now there could be some negative angle that we don't care about. It would correspond to maybe 3 theta equal to that, equal to negative pi. Like I said, if we only consider the positive angles starting from 0, well, we get this sequence of solutions which correspond to angle here, angle here, angle here, r is 0, angle here, r is 0, angle here, r is 0. Now, for our purpose, we're going to pick up the first two because clearly it's going to go from 0 to pi over 3. Get back to our definite intervals is a half, 0 to pi over 3. Now shoot. Well, since the pole is at the tip of this loop, we shoot r in is 0, r out is whatever graph we have here. So R out is 3 sine 3 theta square. R in is 0, and this is our definite integral. Simplify it. It's 9 sine square theta d theta. To evaluate, this is a simple trig integral. Do a substitution first, because we're going to apply formula immediately. This is 3 theta we'll take care of. Just say 3 theta equal to u, simple substitution, 9 over 2, pour the 9 out. With the substitution, we're going to have 1/3. So basically, it's a sine square u du. Apply the formula. 9 3 cross out, so 3 over 2, 1/2 u minus 1/4 sine 2u, or 1/2 times 3 theta, 1/4 sine 6 theta. So u is 3 theta. And then plug in pi over 3, plug in 0. With the calculator, be able to find your answer. 3 theta, 3 theta pi over 3, plug in for theta is 2 pi, which is 0. In plugging 0 for theta is 0 is 0. Well, it turns out it's actually not bad. 3 pi over 4. That's the area of one loop. So in the beginning of this example, you see how we determine basically the angles involved. We got the inspiration by looking at the graph. The graph, the angles, whether it's here, which we didn't know, we were not very sure, look like a 0, and there's an angle here. Again, it was not very clear whether it's something between 0 pi over 2 or it's actually pi over 2. But what was clear was R is 0. So whether you're looking for angle here, angle here, angle here, you set R equal to 0, which means you have to solve a trig equation. With the help of graph sign, I determined a sequence of solutions. Those are all solutions. Now which pair should be used? Look at the graph. It makes sense to have reasonable guess that 0 must be this angle, or pi over 3 must be this angle, 2 pi over 3 must be this angle. So from this order, we pick up 0 pi over 3 as alpha beta. Now you can see, if for some reason you want to work with the second paddle, you want the second loop, so I want to find the area of this region. According to the answers, according to the order, then you can tell your alpha would be this guy, green, that's 2 pi over 3, and then this beta angle, you're working with this loop. Your alpha is 2 pi over 3. Your beta will be this angle. What is that? Is that a pi? Well, don't just guess. You would have to actually get another solution. 3 theta equal to 3 pi would be here, and it turned out, yeah, indeed it is pi. So you would use those two, the third and the fourth solution, as your alpha beta respectively. Alright, either way, once you find your alpha beta, then you should to determine your R in R out, set up integral, which usually is a trig integral. Let's see one more problem where we have to graph again. Graph is not given. In this example, we're supposed to find the area of region described as inside graph of one polar function and outside graph another function. Well, first thing is to come up with the graphs and identify the region. Start with r equal to 2 plus cosine. What's the graph of this? Well, not clear. We'll just have to kind of do the table again. This time we're going to get all the details, get some estimate. Let's see. Start with the theta equal to 0. Theta equal to 0. This is 1, so it's a 3. So 0 r is a 3. Let's pick up, say, theta equal to, again, pi over 3, because 60 degree, I know cosine is 60, cosine is half. So at 60 degree, it's half, so it's 2.5. This is 3, 2.5 is a little shorter. Say 3 is here, the 2.5 is here. Then I pick up pi over 2. Cosine pi over 2 is 0, so it's even shorter at the 2. So 3, 2.5, 2. Now, if theta is pi, cosine is -1, so the sum is 1. Let's say here. Well, I pretty much get the idea. Okay, starting from 0, pi over 3, 2 pi, pi, and if you continue, you're going to see a graph like that. What is this? Is this a circle? I don't know. I just know it's a closed loop. So this is pretty much done through a table method. Now r equal to 2. R equal to 2. This location actually is precisely 2. This is 1. This is 3. Therefore, r equal to 2 we know represents a circle. Would look like this. Now we can guess the intersection of those two graphs is probably at here. We'll actually do some algebra to confirm that. You'll see it's very important we get correct location, accurate angle. Anyway, r equal to 2 plus cosine theta is this loop, closed curve, whatever it is. R equal to 2, we know is a circle. Now, where's our region? It says the region is inside this guy and outside the circle. Therefore, it's this. This is the region. We use chopstick to try to pick it up. One chopstick is placed here. What angle? Not clear. My guess is negative pi over 2, but we'll actually find out what it is precisely. Another chopstick will be here in order to pick up this creaser shaped region. So first, let's determine the angle here and the angle here. And those two angles will give us the same R values no matter which R you pick up. So that's intersection. Because of this, we set the two R's to equal to each other. We set 2 plus cosine 2 equal to r equal to 2 and solve this equation. Whatever theta will give us the angles where the two r's are saying intersection. This is a simple equation. Even simple, I still rely on graph. From the sketch, I expect a negative angle here, a positive angle here. Now the solution I have, well, it's going to be pi over 2 and the negative pi over 2. So the graph is kind of ugly. This would be the y-axis, it will be x-axis. So I can tell clearly from the graph of a cosine, there's a negative pi over 2 is a solution, positive pi over 2 is a solution, and that indicates this angle is indeed negative pi over 2, this angle is positive pi over 2. Now I'm ready to set up the integral. Half alpha to beta. Remember, whatever angle you pick up, your alpha is less than beta. When you solve the equation or look at the graph, once you're sure actually this angle is negative pi over 2, then you can also say this angle is 3 pi over 2. This angle can be 3 pi over 2. But if you can use a 3 pi over 2 as your alpha, your beta will be pi more than that. It'll be 5 pi over 2 up here. Alright, this way to ensure beta is always greater than alpha, because the angle, this is how we always rotate theta. So you can use negative pi over 2 to pi over 2 or 3 pi over 2 to 5 over 2. Of course, this is simple. Anyway, so get our alpha beta. Now, R in, R out, how do we do it? Shoot. Stand here and shoot. This is R in, that's actually a circle. This is R out. So R out is 2 plus cosine theta squared. R out is 2, so it's 2 squared. And this is the formula we derived earlier, actually in the beginning. Half alpha to beta, R out squared, R in squared. The rest is just to evaluate the integral. Do the algebra. It's a 4 plus 4 cosine theta plus cosine square minus 4 d theta. This 2 4's cancel each other. Find the antiderivative. That's sine and cosine. We actually had this before. It was half theta plus 1/4 sine 2 theta. Just plug in this time. I'm not going to do it. Just plug in pi over 2 and plug in subtract. Alright. So we see how we had to graph involved polar functions, polar equations by hand, by table method. In article 0, article 2 was simple. We know that represent the circle. We didn't really struggle at all to get the graph. This one, well, kind of pick up different angles to get the sequence of points to trace out the graph. Once we have the involved graph and identify the region inside this loop, outside this circle, Then we set the two r's to equal to each other to determine the angle here and the angle here. So set the functions to equal to each other and solve to determine angles involved, alpha, beta. As you can see, if we place chopstick, one chopstick down here, another chopstick here, to try to clamp the region. Then shoot. Now, speaking of shooting, it helps to try to vary the angle along which you shoot. Sometimes it's a different. In this example, it's not. No matter where we shoot, we always hit a circle, R in, and this guy R out. All right. So we determine R out square, R in square, and simplify, evaluate. Now, let me show you a situation where, say, you have a loop, let me say circle, larger circle up here, right? Suppose we say, let's find area of the region inside both loops or both circle. Well, it will be this region, right? Actually, let me use a different color so you can see better what I'm trying to talk about. Say this is a green. This is blue. We assume they're both circles. Doesn't matter. I want to explain the idea. This is a pole. Now, it's clear the region is here, right? Suppose we even know the angle is 0. If this is a circle, this angle is 0. This angle is pi over 2. That's no problem, right? So we would set up our, say this is a R small, R large. So we would set up our actual integral as half angle 0, angle pi over 2. Say we would say 0 to pi over 2, apparently, right? This is kind of chopstick. 0 here, pi over 2 here to clamp this lemon-shaped region. Now, after we determine the angles involved, we would shoot to determine R in, R out, right? Well, let's see. We always shoot from the palm. We shoot. It looks like R out will be the green one if we shoot here. The problem is, if we shoot from different angle, some angle close to 0, say close to the polar axis, we will come out from the blue one. So there are two different R's. That means we cannot simply set up one integral 0 to 2 pi for area of this region. We need two separate integrals. As a matter of fact, we would have to find this angle. As smaller this angle, when we shoot, will come out from the blue one, the larger circle. Greater than this angle, when we shoot, will come out from the green one, the smaller circle. This is why I said, even you see the region, you need to sometimes, take a, just a little time to vary the angle along which you shoot to determine the R in, R out. Like in this case, it's complicated. If you shoot within this range, you can hit the smaller circle coming out. the region we call the R out to be shoot up here. You're gonna hit the blue one. Oh, I'm sorry. Here's here's the blue one. Here's the green one. So you would have to set up two integrals. The key is to first of all determine the angle. Now this angle, well, how do you do that? You notice this is where the two graphs intersect with each other. So you would set R large to R small. Find the corresponding angle. One angle is going to be 0 for sure because this is intersecting to. So we're interested in this angle. So there will be two solutions as we see. So we expect two solutions. One is 0. One is whatever angle we are actually interested in. Hypothetically, we find the angle to be pi over 6. It would mean we're going to do 0 to pi over 6, taking care of, let's say, this kind of blue shaded region because it's a blue border. So 0 to pi over 6, this region. RL, the key is RL is this blue one. RL, the larger circle square minus, well, R is 0 as 1. Then pi over 6 to pi over 2 as the other one for the, say, green shaded region because the border I use green color. So we would have to do two integrals. Now this situation just shows you whatever region you come up with, you determine alpha beta, and you determine R in R out by shooting. When you shoot, just take a little time to see if there's any complication like this. Alright, well, whatever case, you have the graph. Alright, get the graph, then you find your region. So this is error computation in polar coordinate.